So today we are still continuing with dynamic programming. This will be their last lecture on it finally. So you should be able to solve some problems using it. So today we will talk about, we will continue the previous lecture and we will come forward with their dynamic programming on profiles. So consider their question. You are given graph so it's a little bit on graph theory, but you shouldn't much worry about that. I will explain how to solve it and we will talk about that. So do you know what Hamiltonian path is? So Hamiltonian path is a path on a graph that visits each node only once. So for example, here we can go here, here, and here, and we stop here. So if we want to start at one vertex and we want to end at the same vertex, then it is Hamiltonian cycle. So this is the Hamiltonian path, where you start somewhere and end somewhere. So this problem to find the Hamiltonian path is NP-complete. This means that there doesn't exist any polynomial algorithm that works, that solves this problem. Okay, so since it is NP-complete, we can suggest that we can solve it using using the exponential time. We talked the last time about the dynamic programming on masks. So where the state were some binary mask, whether we took some element or we don't take some element. Do you have any ideas on how to solve the problem with the Hamiltonian path? So we have to find the Hamiltonian path from the vertex, I don't know, 0 to the vertex 1. Whether there exists such Hamiltonian path in the graph, using the masking, dynamic programming on masks. Any ideas on what it can be? So we have dynamic programming.
Please give us 15 seconds.
Okay.
just like make a list of every connection between the vertices?
Yes, sure. You're given a list of all the connections, or like you can have an adjacency matrix, rather than like you can have adjacency matrix if you want. Like,
so yeah, we have like the list of visited vertices, and before adding the vertex to the list, we check if it has a connection with the vertex that hasn't already in the list of visited vertices.
Okay, it is almost true. So dynamic programming will be of mask, and you add a new vertex there, right? So you add a new vertex, add vertex v, but when we can add the vertex v there?
What was the question again?
When can we add the vertex v to this mask?
If it has the connection with the vertex that hasn't been added to the list.
That hasn't been added to the list, or that has been added to the list.
Okay, maybe it has.
So, like, can you tell me what will store in this dynamic programming mask? What you will store there? What it will be? So you want to add a vertex v to get what? So you have.
Please, like, rephrase the question. I don't got it.
Okay, so dynamic programming typically gives some sense. For example, like the last time when we talked about the knapsack, we told that dp of mask is the minimal number of knapsacks we need to hold all their elements there. This was the dynamic programming.
Just all the vertices, I guess.
What? Sorry?
All the vertices?
No. What this dynamic programming is itself? What does it mean? What does it mean dp mask? What it will hold? What it will hold inside it? Either there is Hamiltonian path on these vertices, or something like that. What is there? What is the sense behind this dynamic programming itself?
Well, if I've got it right, the sense is to find the path that has all the vertices.
Yeah, the final answer, yes, the path through all the vertices. Then what is this dp is? So for, like, I understand that if we take the mask as all ones, then your answer will be dp 1, 1, 1, 1, 1, 1. But what is dp depending on the mask itself? So you're given dp mask. What it should be equal to? What do you expect from it?
Isn't it like the array of vertices, like the path? Maybe I've got it wrong.
So you want in dp mask the array of vertices? What? I don't think that I fully understand. I mean, you're in the right path anyway, but like you should be able to state what dp mask is. So dp mask, this means like it is dp of some vertices, right? v1, v2, vi, something like that. So it is dp of some subset of vertices. What it is? Okay, let us think a little bit more, and like then I will explain.
Is mask of the path?
No, you're trying to ask question. Like I'm asking for the answer. So what dp? So what dp of mask should be?
It should be the path.
It should be the path. Okay. So
Process 1, we have all the vertices listed, and we can turn them on and off with a mask.
Okay, yeah. So the dp should be something like that. Can we have a path that visits only these vertices? So that there is a way that you can reorder these vertices. So the first one will be connected to the second one, second to the third one, etc. And ith minus 1 to ith. Yeah. So like as Ekaterina told us, like she wants to add a vertex v to this path. However, what is the condition under which you can add v to the path?
If it has not been visited.
Yes, but what else?
And it also has the connection with the vertex that hasn't been visited also.
And more. So here in this dp mask you may contain some path there, and you want to add vertex v here. So
it should have a path to this vertex.
Yeah, to which
we added.
Okay. Probably I'm again like waiting for the right answer. So you want to add v to the end of the path to increase the path. V should be connected to the last vertex on the path. Okay. So
it's connected with the end. Okay.
Yeah. So mask is not enough for us. Because when we know that if there is a path from this mask, we don't know the last vertex on this path. So we cannot add it. So for that specifically, we update our dynamic programming to this. Is can we have a path from mask and ends on u? That is when you will iterate through all your dynamic programming thing. You want to try to add B, and you need to check two conditions. It doesn't lie in the mask, and it is connected to U. That's it. So the algorithm will be the following. For mask. So this is everything that you need to be done. So you iterate through all the masks from their lowest to the highest. And you iterate over all the possible ends of the path. And if you can achieve the path for this subset of vertices with the end, you iterate over all next vertices and check. If it doesn't belong to mask and there is an edge between and next, you update like the mask. You update the mask. You add next to the mask, and you change like the next now is the latest node on the path, and we set it to true. Okay? Is it clear?
Yeah.
What is the complexity of this algorithm?
O squared? N squared?
No. So I'm getting answers. So O of n squared. Okay. Are there any other attempts? It is trivial, guys. You should be able to do this. How many loops do you see there?
Three loops.
3 loops, okay. So what is the complexity then?
The first one is 2 in the power of n.
Okay.
Multiplied by n squared.
Yes, that's exactly. I don't know why did it took like a lot of time for you. You should be able to do this like with the flick of the finger. Like this. It is not hard to see that. It is the outer loop is 2 in the power n. Like this cycle is n, this cycle is n, so like you just simply multiply all these values and you get n squared times 2 in the power of n. Okay, good. So like this problem is reasonable to solve, like where n is approximately like 20, something like that. Because when you add like 20 here, it will work. The total complexity will be, I don't know, something. The total number of operations will be approximately 4 times 10 to the power of 8. Like if you put n equal to 20. And this total number of operations typically fit in 2 seconds. But in general, like you should be able to understand that you shouldn't take n too big, because like n30 probably will be much than you expect to calculate in the reasonable time. Because if you put n30 there, then like there will be something. Okay. The question is, can you update this algorithm to this complexity, where m is the number of edges? Like you can change the way you store the graph.
Well, if we store the edges and then we sort them somehow. Just let me. I'm thinking aloud. Okay. So yeah, we store the edges and we sort them.
Okay.
And then we do basically the same thing. We check the first and the last value. Okay, I'm thinking, still thinking.
So, okay, let's think a little bit. We have like today we have time, so I'm not going to rush anywhere. Like we are almost close to an end of dynamic programming. So like, let us try to understand. Like, let us play a bit with algorithms. So yeah, that's a good start. Like let's have an array of edges, or list of edges, or
So yeah, basically one of the thing would be that the last value should be the same as the first value of the second edge, like we wrote in the mask before, and it's basically the same, I guess.
Sorry, didn't get it. Can you try to explain again?
Okay, I will try to formulate it.
Okay. Okay, did you come up with the possible algorithm? So let me do this then. I will erase this. I will count that for E in E. And equals here dot U next equals E dot V, and if and is not in the mask and not a mask. Oh, not a and not DP mask. And then continue. So you simply traverse over all the edges there and try to relax the dynamic programming over this edge. So we take the and in the next, as in the previous algorithm, we take and at the start of the edge and take next as the end of the edge, and simply if and is not in the mask, then we should do nothing. And oh, sorry, or here is or. Here should be or their DP is not true, so like there is no way to get with the mask and this and, then we should also continue, so we shouldn't do anything. Okay, questions here? It seems you're a little bit tired already. After 2.5 months of education, you're already tired. Okay. So this task will be in your homework. Pay attention to that. And finally, we will talk about DP on profiles. So what does it mean? Suppose you're given a table n times m, and you want to calculate the total number of ways to put a dominoes on it. So we can put a dominoes there in such manner. The domino is there like a small rectangle of 1 times 2. So I'm randomly trying to fill it in, and I'm unsuccessful. Because my table is odd. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 6, 7. Yeah. Unfortunately I can't split it into dominoes, but like I hope you get an idea. So the question is, given the table n times m, please calculate the total number of ways to split this table into dominoes. So how would I suggest to solve it? Let us maintain, let us feel the board from left to the right. So we will try to feel them like kind of column by column. And at some moment, so for example, you think that you fully, sorry. you fully filled the first three columns, but there are some dominoes that are coming out of these three columns. Kind of that. Kind of that. I don't know. And suppose here. So, and our algorithm will be like our dynamic programming. It will be column and mask. Can we fit? Can we like the number of times to put dominoes that fit like this, like n column, with the mask outside. So for example, this one will be 0, 1, 1, 0, 1. So it shows you like by this. So you split here, and it shows you what are there taken cells already covered by dominoes. So the question is how to update this dynamic programming. So it is quite simple. You need to understand, can you traverse from mask 1 to mask 2? So for example, here there is only one possible mask that can be next. So it should be like this. You should add domino here and domino here, and you will go from 0, 1, 1, 0, 1 to 1, 0, 0, 1, 0. However, if your previous mask was a little bit different, there were zeros here, you have at least two ways to add dominoes. You either add them like this and get to 1, 0, 1, 1, 0, or you can put a domino vertically there and you will get we'll get 0, 0 here. So at first we will pre-calculate for each pair of masks whether is it possible to get from this mask to this mask by adding the dominoes. So we kind of feel, we've tried to fill the next column fully, and we will look which masks can we get out of that. Then the algorithm becomes pretty simple. You just iterate over all columns and masks and try to get the next mask simply. You try to simply get the next mask, like you traverse column 0, M, mask 1, 0 to the power of n minus 1, mask 2, 0 to the power minus 1, and you simply like check if can mask 1, mask 2, then update dp column plus 1 with mask 2 plus equal dp column mask 1. So you simply traverse the first part of the dynamic programming and try to update it by the next mask. And you just add equal to this. What is the time complexity of this algorithm?
N multiplied by 2 in the power of 2n.
Yeah, simply m multiplied by 2 in the power of 2n. And where do we store the answer? Which dp is the answer? So we want kind of the answer for, so with this split. Okay, let me do this. It is dp n plus 1 with mask 0. Because if you split here, you want that none of the dominoes are coming outside of the box. So the mask is 0 here. So all the zeros are here. So the answer will be dp of the column, and the column is the next one, with 0 there. Is the algorithm clear, or it requires any detail, like any explanation? Or it is not understandable at all? I'm a little bit worried with your attention this session. It seems you are.
Can you please explain it again, just to be sure that I've got it right?
Okay.
Because I don't know what question to ask.
Okay, so again, let me try from the start. So we will maintain the dynamic programming that will depend on the state as column and mask. And what does it mean? Is there total number of ways to split onto dominoes so that all the first column number of columns are filled fully, and there is some of their next cells already filled by their dominoes, so like the mask elements. So for example, here it was 0, 1. So the column will be 3, and here will be 0, 1, 0, 0, 1. We read like that. So how to update from the one state to another state? We kind of want to to move the column to the right. So we want to move the column here. So we iterate through all the possible masks that will be next after we fill this column. So for example, in this case, we can get to 2 different masks. Like this 0 can be, no way it should be the horizontal domino. Here we have 2 different ways. So we have 1 vertical domino or either 2 horizontal ones. So we do this with this magical function can. Like which we can previously pre-calculate before doing this. So we just traverse through the column, traverse to the mask, and we check, can we get to the next column with this mask? And if we can get from mask 1 to mask 2, we will update the DP, like the next dynamic program with the next column and the next mask, mask 2, plus equals like the number of ways to fill like the previous column and mask 1. Okay, let's hope that you understand that. And then we are coming to a little bit more complicated technique here. You can see that 2 to the power of 2n is very large. Can we do with another profile? Because you see that our transition function for dynamic programming is very huge. We take from this mask to its neighbors, and there can be like the number of edges between masks can be very huge. I mean, the number of pairs such that mask 1 and mask 2 complies with it can be very large. So we will do a little bit different dynamic programming here. Sorry, here one. We will use another profile. So the previous profile was just the column, like the split by the column. How many ones there? Like right now it will be a little bit different. So we will have their curved profile. So it will depend on dp column, dp row, and mask. This will be the number of ways put dominoes to the following. This is the column, this is the row, and the mask is here. So the mask is curved a little bit. So it is like down, 1 to the left and down. So for example, here it will be the number of columns is 3, the row is 2, and the mask is 1, 0, 0, 0, 1. And here you have a smaller number of states. You want to come from this state to the state with only one additional cell. So like instead of this one, you come to this one. So you simply get there and check. There are 2 ways we can put the domino. Either we can put like that, and we will have the mask 1 here, or either you put it downwards and get to the next state with 2. So, and here will be zeros. I'm not asking you to write the code for this problem. Like, if you wish, you can, but like I'm not asking you to do this as your homework because it's a little bit complicated for you. But can you tell me what will be the complexity of this algorithm? So we go over each column, then we go over each row, and over each mask, and we try to update to column, row plus 1, and mask prime, some another mask. And you have only two possible transitions. Either you put the domino like that, or you put a domino like that. Or either you cannot put them if there is one there or one there. So what will be the complexity of the algorithm? We have only constant number of transitions from one state to another state. So what will be the complexity then? Nobody?
Can you please tell? I have no idea actually. Well, I have some ideas, but I understand that they're wrong. Can you please explain the complexity?
Okay, the algorithm will work in n squared, n times n times 2 in the power of n. Because you iterate over column, you iterate over row, you iterate over mask, and then you have two ways of transition. Either you put a domino like that, or you put a domino like that, or you cannot put a domino anyway, and you just move it to the next. If it was 1, then you just move it to the next. Okay. Let us think that we solved a little bit different problem. If you don't have questions about the current problem, then I will move to the next one. You again have a rectangular grid of size n times m, and you want to find the number of colorings in black and white. Each cell you can color in black or white. The number of colorings such that there is no rectangle, no square 2 times 2 filled with the same color. To solve it, we will do the same dynamic programming with profile with a little difference. So it is again 1, 0, 1, I don't know, like 0, 1, 1, 0, 0. The only difference is that right now we will store also the state of this rectangle, of this cell, sorry, not rectangle, of this cell. So we will store the mask of size n plus 1. So we store this, and this, and this corner cell, which is in our corner. So and then we can simply check to which color we can color this cell. It can be 0 or 1. For example, if here was not 0 by 1, but 1, then this cell cannot hold 1. It can only hold 0. So we just add 0 here and we move to the next state. And like that, one by one, you will be adding the cells to the coloring and like to the mask. And that's it. So it's a little bit different problem, but it is almost the same. Okay, questions about that? Or you need to have some time to think about it?
I think we can move on.
Okay. Good. Okay. So kind of that's it with dynamic programming. So I explained you almost all the tricks that can be solved by dynamic programming. Oh, can you tell me the complexity of this algorithm?
Is it the same as previous one?
Yeah, it is the same as the previous one. Yeah, that's right. So that's almost all with the dynamic programming. Let us try to solve the problem that is coming to be in your homework. Let us, like, this is, I think this is a little bit complicated for you, the last parts with dynamic programming on profiles and etc. It's a little bit complicated, like let's come to the simpler things. So you're given a string. And you want to calculate the total number of times how much ABC is a subsequence. You need to calculate the number of times like you're given a string and you need to calculate the number of times where ABC is a subsequence. Not the substring, so it shouldn't be like in their neighboring cells. For example, this ABC is a valid subsequence. So you need to calculate the total number of ABC as a subsequences. How would you solve this problem?
May I ask you, when we start from one of A's, we can choose, actually, we can go this way, we can start from unique A's positions and calculate if B, C is after them.
Okay, but how do you calculate the total number of ways? You don't have to check that ABC is a subsequence. You need to calculate the number of times it appears as a subsequence.
I will go through all the A's.
Okay.
From left to right and calculate.
Suppose you go by each A, yes, and what you are doing next?
Then check if when you start from A, you check if, I think it's the best way to solve it, but you go and check if B is present and C is present somewhere next. If it is, you check that it is present as a subsequence and move to next A. But it will not count if.
Yeah, but for example, for this A, there will be two. There will be ABC here and also ABC here.
Yes, but that's why I was asking first time. Do we calculate both of them as a?
Yeah, we calculate both of them. Yeah.
Oh. So since we have three letters, when we check from each A, we check for the B, and from each B, we check for the C, and we do it recursively.
Okay, what is the complexity of this approach?
Something such.
Precisely, can you tell me precisely what will be the complexity? So if the length is n.
Yes.
What is the complexity? So yeah, we can go over all A's, then for each A we will traverse for all the B's, and then for each B we traverse over all C's.
Since we check every cell, maybe this will be n times by Well, we need subset them something. N minus n and n minus 2. And maybe divided by 2.
Okay, so what is the complexity?
Looks like n cubed some sort.
Yeah, exactly. It will be n cubed. In the worst case. In the worst case, it can be n cubed. Okay, that's a good start. But I claim that it is possible to do it in linear time. So let us do at first. Can you get rid of one cycle, Elizaveta? One loop. Get rid of one loop. With some pre-calculation. So like you traverse over all A's, you traverse over all possible B's, and then what will be like when you traversed over A and B? What is the total number of ABCs for this A and B?
In this example?
No, not in this example, in general. So you fixed A, you fixed B.
Are all possible C's that are after B?
Yeah, that are after B. So like it is simply the total number of C's on the suffix.
Okay.
Okay, so you can pre-calculate
Suffix.
like for each suffix, and then you just traverse over A, traverse over B, and then you increment it by the total number of C's on this suffix. Okay. That's the first step. So we get from cubic to squared using that. Can we do similarly further? Can we reduce the complexity?
Maybe I'll listen to you, so yes, but...
Yeah, but how? So here we pre-calculated the total number of C's on the suffix. Can we do something similar so we can traverse through A and then like add the total number of BC's on the suffix? Like,
yes, we can do this.
how we can do this?
When I'm trying to do this in my mind, it's going well.
Isn't it like the same?
How? The same how?
Maybe if it's the same, how it goes.
Like if we start like with the A, for example, in the fourth A, we only check for B's and C's after this A, and just the same algorithm, but applies to further to.
Yeah, but the question is how to calculate the number of BC's on the suffix. So yes, we iterate over A, and then we have to calculate the total number of BC's as a subsequence on a suffix. How can we do that?
We can go.
Okay.
what we started, we can go recursively, like we were trying to. I was trying to calculate ABCs, like A, when for each BC, calculate BC, but now we calculate for each B, we calculate C. So, yes, we have a subset with BCs. When we go for each B and calculate number of C's that it out and go for the next B with sum up. When going back and return this number for A.
Okay, yeah. So like you calculate for, like at first you calculate the number of BCs on the suffix. So you just go from right to the left, you take B and calculate the number of C's on the suffix. So it will be 1 here. Then you go to B here, and there are 3 C's on the right. So we put 3 here. And then to calculate the number of BCs on the suffix, you just go from right to left in this array where we calculated, and then we add the suffix sound on it. So it will be 0, 1, 1, 1, 1, 1, 1, 4, 4, 4, 4. And then when you ask for ABC, so we already know the number of BCs on the suffix. So when you ask for ABC, you just go over all A's and add it like from this array, from the second array that we calculated, the number of BCs on the suffix. Okay, is it clear?
Yeah.
Is it clear that we can do this with the same number, like not only for ABC but for A1, A2, AK? So if it is not ABC but like K different characters.
It looks like we can do this, at least we should.
So your dynamic programming kind of will be the same. You just want to calculate on each suffix the number of ways to pass like the suffix of this thing. Like dp S1, S2 is the number of occurrences of AS2 AK in T TS1 TM. And you can do this by adding each time the new character to the left. Okay. That's it for today, I think. If it is clear, like this, like what is going to be in this homework. So in this homework, you will be given the Hamiltonian path. You will be given this problem, and there is another problem which is quite simple also, but for on dynamic programming. And I would like to ask you to solve all of them. There will be I will try to be gentle this time, and I will not give any more simple task as the first two problems. Like, let's try to solve at least the problems that are given. Okay? So, thank you very much for coming. See you next week.
Thank you.
Thank you.
Thank you.
Bye.